Okay, so this video is going to be about pH, pKa, all of that goodness. So first off, what is pKa? Well, pKa is a dissociation constant, particularly of hydrogen ions. If you think about pH, that makes sense, because with pH, we're mostly concerned about the concentration of hydrogen ions anyways, so it just makes sense that in dealing with pH and pKa that we're concerned with the ability of hydrogen ions to dissociate. So, a little rule of thumb, as pH decreases, acidity increases. That's something we're all probably pretty comfortable with at this juncture. But as pKa decreases, acidity increases. So a strong acid, don't do this, will have a low pKa, and a strong base will have a high pKa. Alternatively, if a strong acid has a low pKa, a weak acid will have a higher pKa compared to a strong acid. And if a strong base has a high pKa, a weak base will have a lower pKa than a strong base. So what does all this mean? Right now it probably just sounds like words, so let's kind of go into the definition of what an acid and a base is, because I think this will clear some things up, and then we can relate it all back to pKa. So the Bronsted-Lowry definition of an acid is that an acid is a hydrogen ion donor. That is to say that an acid wants to get rid of as many hydrogen ions as it can. Or maybe it has a greater ability to get rid of its hydrogen ions, would probably be a better way to say that. So if that's what an acid is, if an acid is a hydrogen donor that has the ability to get rid of its hydrogen ions, a base is probably the opposite. A base is going to be a hydrogen ion acceptor. And that definition might be a little fuzzy because the word acceptor is a little bit passive, and bases tend to have a bit more of an active role. So an alternative definition for a an alternative definition for a base could be that a base is a hydrogen stealer or taker. And it's going to want to hang on to or grab hydrogen ions. So relating this all back to pKa. Knowing that an acid is a hydrogen donor, it has the ability to get rid of its hydrogen ions. A strong acid will more fully adhere to the Bronsted-Lowry definition of an acid. So this might be a bit of a confusing sentence. We use these definitions of acids and bases as acids are hydrogen donors, bases are hydrogen acceptors, and that's all very cut and dry. But as we know, biology, life, chemistry, all those things in general tend to be not so cut and dry. It tends to be in degrees. So what we're saying here is that a stronger acid will more fully fit the definition of a hydrogen donor, whereas something that's, say, a weak acid might not be as good of a hydrogen donor. That's all that this is saying. So a strong acid will more fully adhere to the Bronsted-Lowry definition of an acid. So far, so good. And so all of this is to say that it is really, really good at ditching. Ditching. What is that? That's not a word. It's really good at ditching its hydrogens, its hydrogen ions. So the key take-home point here for pKa and acidity, especially in respect to the Bronsted-Lowry definition, is that strong acids have a low pKa value because it really doesn't take as much for hydrogen ions to dissociate. So it doesn't take much at all. So thinking back to the Bronsted-Lowry definition of an acid, if it's already pretty much willing and able to get rid of its hydrogens, those hydrogens will just pretty much readily dissociate, is all that that's saying. It's not going to take much for hydrogen ions to dissociate from acids. But for bases, of course, it is the opposite. So, in relation to the definition of a base, a strong base will more fully adhere to the Bronsted-Lowry definition of a base, whereas a weak base might not as fully adhere to the definition. So a strong base is going to be a hydrogen acceptor, or as we've discussed, a hydrogen taker. It will hold on to those hydrogen ions. It's a hydrogen ion hoarder in some cases. So this means that our Bronsted-Lowry base will be really good at grabbing. It will be really good at grabbing, or alternatively, it will be really good at hanging on to hydrogen ions. Let's try this again. So our strong base will more fully adhere to the definition of what a base is, in that it will be really good at grabbing or hanging on to its hydrogen ions. It's not going to those hydrogen ions aren't going to dissociate as well as the hydrogen ions on the acid. So the key take-home point for bases is that a strong base will have a high pKa value because it's really going to take a lot more for those hydrogen ions to dissociate. It takes a lot. So in this way, you can think of pKa values as like the threshold at which the hydrogen ions will dissociate. So acids, because by definition they aren't as good as holding on to hydrogen ions, their threshold is much lower, whereas bases, which by definition are really good at hanging on to hydrogen ions, their threshold will be much higher. It's going to take a lot more to pull those hydrogen ions off. And that's all I have for you for this video. In a future video, I intend to apply this to a couple of molecules and some amino acids and to demonstrate how you might be able to guesstimate the pKa of certain amino acids.